everyone, welcome to our video presentation. Today we're going to explore Hess's law. So, have you ever wondered how scientists determine the energy changes in chemical reaction without directly measuring them? Well, that's where Hess's law comes in. What are we waiting for? Let's dive in!
Hess's law states that the total enthalpy change of a reaction is the same, no matter how the reaction takes place, as long as the initial and final condition are the same. In other words, we can add up the multiple reaction steps to find the overall enthalpy change. To put it simply, Hess's law works because enthalpy is a state function. It depends only on the initial and final states, not the path taken. Now, let's see a real-life example of this principle.
So, Hess's law was formulated by German Hess, a Swiss-born Russian chemist, in 1840. So, his work laid the foundation for thermochemistry, helping scientists understand energy changes in reaction.
Okay, so now that we understand the concept, let's apply it to a problem. So we'll go through a step-by-step solution to see how Hess's law works in calculations. So let's calculate the enthalpy change for the following reaction. So we have here 2 carbon monoxide plus oxygen gas leads to carbon dioxide, and the enthalpy change is equal to negative 566 kJ or kilojoules. And this following reaction is what we call direct path. To solve for the enthalpy change, we could use some identical reaction to the chemical reaction, and this refer to the indirect path.
So let's solve this following reaction. We have here the direct pathway. 2 carbon monoxide plus oxygen leads to 2 carbon dioxide, and the enthalpy change is equal to negative 566 kilojoules. We also have the indirect pathway. So step 1, we need to manipulate given equation to resemble equation of interest most closely. Perform same operation on enthalpy change as on equation. As you can see, the 2 carbon monoxide in the direct pathway is in the side of the reactant, and the 2 carbon monoxide in the indirect pathway is in the side of the product. So we need to reverse this equation to match the target reaction. But what is our target reaction? Take note that our target reaction is always the direct pathway. So go back to the equation. From 2 carbon plus oxygen leads to 2 carbon monoxide, it will become 2 carbon monoxide leads to 2 carbon plus oxygen. Since we reverse the reaction, we also have to reverse the sign of enthalpy change from negative 221.0 kilojoules to positive 221.0 kilojoules. Always remember that when we reverse the reaction, we also have to reverse the sign of enthalpy change. Now let's proceed to the second equation. We have here carbon plus oxygen leads to carbon dioxide, and the enthalpy change is equal to negative 393.5 Since our target reaction involves 2 moles of carbon dioxide, we multiply the entire equation by 2. So it will become 2 carbon plus 2 oxygen and leads to 2 carbon dioxide. The enthalpy change also gets multiplied by 2. So it will become negative 393.5 kilojoules multiplied by 2 is equal to negative 787.0 kilojoules. Take note that when you multiply the entire equation, you also get to multiply the enthalpy change. Now let's proceed to the step 2 by adding the modified equation. By adding these equations, the intermediate substance cancels out as it appears on both sides. Since enthalpy is additive, we also sum the enthalpy changes. 221.0 kilojoules plus negative 787.0 kilojoules. And the answer is negative 566.0 kilojoules. Therefore, the enthalpy change for the reaction 2 carbon monoxide plus oxygen leads to 2 carbon dioxide is enthalpy change equals negative 566.0 kilojoules. This shows how Hess's law allows us to determine enthalpy changes using an indirect pathway.
Did you know that Hess's law is used in industries and everyday life? For example, in food science, we use it to determine the energy content of food. Hess's law is also crucial in designing fuels and predicting energy efficiency in engine and power plants.
So, let's take a small experiment. This is a burning candle. The burning candle represents a combustion reaction. So Hess's laws tell us that no matter the change of the energy, it will always remain the same. That's all.
Good day everyone. Hess's law can also help us to understand energy transfer in nature, like the process of photosynthesis in plants. Even though we can't directly measure all the energy changes, we can use Hess's law to estimate the total energy absorbed and released during these natural processes.
In the real world, Hess's law is used to optimize energy efficiency in industries. For example, in chemical production, it's used to estimate the heat involved in reaction, helping companies reduce energy waste and lower production costs.
Hess's law also plays a key role in developing clean energy technologies. By understanding energy changes in chemical reactions, scientists can design more efficient, renewable energy systems like better solar cells and fuel cell, which are crucial for a sustainable future.
Hess's law is important principle in thermodynamics that states that total enthalpy change for a chemical reaction is the same regardless of how many steps the reaction takes. This means that even if measuring the enthalpy change directly is difficult, we can calculate it using known values from related reactions. It helps chemists understand the individual steps in a multi-step reaction and emphasizes the enthalpy state function, depending only the starting and ending states. These principles also allow scientists to predict whether a reaction will release or absorb energy, which is crucial for assessing reaction feasibility in both education and industry. Hess's law serves as a fundamental tool for understanding energy changes in chemical processes and optimizing them for efficiency and cost effectiveness.
Okay, so to wrap up, Hess's law is an invaluable tool for solving complex thermochemical problems. It allows us to calculate energy changes in reactions, whether they occur in one step or many, and its application range from industrial processes to environmental protections.
So, to recap, Hess's law helps us to determine enthalpy changes through indirect calculations, making problem solving easier and energy calculations more efficient in real-world applications. We hope you learned something valuable today.